A very warm good morning to all. I, Dr. Nishant Kumar, host of the day, welcomes our speaker for day 4, session 7, Dr. Navneet Gupta, professor and head of the EEE department, BITS Pilani, who is a renowned professor and academician in modeling and micro nano electronic devices. Now I would like to request FDP coordinator Mr. Rajin Singh Sikhawat to welcome our distinguished speaker with a bouquet. Dr. Navneet Gupta is a professor and head of Electronic and Electronics Engineering Department at the Birla Institute of Technology and Science, Pilani, Rajasthan, India. He joined the institute in the year of 2005 and became full professor in year 2021. He was Associate Dean of Sponsored Research and Consultancy Division at the same institute during the 1822. He was visiting professor at National Taiwan University of Science and Technology, Taiwan, during May-July 2014. Professor Gupta has research interest in the area of modeling of micro and nano electronic devices, flexible and variable electronics, computation material, science and electromagnetics. He has published more than 100 research papers in the national and journal of high repute. He has also presented 65 plus papers in various conferences in India and abroad. 8 PhD students have been graduated working under his supervision. Professor Gupta has received research funding from various government agencies, which include UGC, DST, SERB, DRDO, and MHRD. He completed 2 international projects, one with University of Sofia, Bulgaria, and another with Tel Aviv University, Israel, in the area of flexible antennas and nanosensors. He has authored 5 textbooks in the area of electrical engineering, engineering physics, and material science published in international and national publishers. He received Professor S.S. Rangathan Memorial Teaching Excellence Award 2022, Outstanding Engineering Service to Society Award by Institution of Engineers, India, DST Young Scientist Award in Physical Science, Gold Medal in Master Degree. He is a Fellow of Institution of Engineers, India, Senior Member of IEEE and Life Member of Semiconductor Societies of India, Material Research Society of India, and many more. So I would like, without any delay, I would like to invite Professor Navneet Gupta to dais for his sharing his excellence.
Hello. Okay, it's fine. Okay. So thanks for the introduction, and I thank the organizers for inviting me for this talk, which is under the FDP program sponsored by the EICT. So the title of the talk is 2D material-based flexible electronic devices. Now, the talk which is actually related to the FDP is slightly different as compared to the research talk, because here the students as well as the faculty used to participate, and the focus should not be mainly towards the research but also towards the teaching aspect. Okay, so there are institutes where they have the flexibility to introduce new courses, and there are institutes where the flexibility is not there. So what they can do is that the courses that they are teaching related to that field, they can introduce few concepts so that the student can get some idea about what is the cutting edge technology that is actually being there. So that is what the purpose of the FDP is. So yeah, so first of all we should be knowing that what is actually the flexible electronics. So basically this field is kind of a very rapidly growing field and is going to have very significant impact on the human societies around the world in coming years. So basically, how this traditional electronics and the flexible electronics is different than the traditional electronic, that is in the important thing. And if you go through the kind of a formal definition of the flexible electronics, so this is actually where you have a different kind of the components and the circuits, and that is actually being fabricated on flexible substrate, because the application part of the flexible electronics is for the wearable application. So you can see that the definition goes like this. So this is the technology of assembling electronic components and circuits by mounting electronic devices on flexible substrates. And the because of for this you can say the when you are installing that on the flexible substrate, so you can have these devices bendable, rollable and foldable, so that it can become a user friendly. To give a few examples, you can see that now in future you will have a display skin that is flexible and foldable. Okay, and in fact we have started looking into the advertisement that is coming for the television, that when you are not using those television, you can press the button and that will going to fold, and you can do that. So that is all possible when you have a flexible display. So therefore this flexible electronics is very important. So these are few examples of the display of the flexible mobile screen. Similarly, you have solar panels. Initially we used to have a huge solar panel which is actually installed on the roof, but with this technology you can have these panels which are foldable. So when these are not in use, you can just fold them. Okay, and also this flexible electronic devices are used as sensors to measure the wrist pulse, and these have a lot of other application in the wearable technology. The demand, as I said, the demand of the flexible electronics is actually increasing day by day, and you can see that now by using the flexible electronics, you can just develop the electrodes out of that to measure the EEG, that is to map the brain activity, and after that you can also have that on the EOG to trace, to read the eye activities, and also the kind of the ECG. So ECG is very common, we all know, is used to measure the cardiac kind of an activity and other kind of patches. So you can see that when you are installing anything on a body part, so it should be conformal. The rigid devices cannot actually fulfill those requirements, so it has to be flexible. So you can see that a huge kind of the application area goes towards the healthcare sector. On the consumer sector, you can see that you have a lot of smart devices that are coming, like virtual reality devices. Then you have energy devices. In energy devices, already I have shown you the solar cells are there. Then you have the flexible batteries that are coming, and the supercapacitors are also uh, uh, because whenever you have a device, you have to give energy to those devices, from where it will be coming. So the energy sources should also be flexible in that sense. So that is another area. Smart watches, smartphones. So you can see that this area is having a huge potential to create the considerable amount of the footprint in the market all over the world. Another example you can see from here, that this actually shows a kind of a schematic to monitor the or you can say to sense the physiological parameters like heart rate, respiratory rate, that is actually placed here in terms of the various sensors, and simultaneously transmitting the data wirelessly into the cloud server. And any abnormality that is being observed, because here you have installed one you can say the sensor which is a human motion sensor, and these are for the heart rate and the pulse rate. Any abnormality that is actually being observed here can be that information, that data can be sent to the family or to the emergency, and the quick action can be taken. So here you can see that this field, flexible electronics, is not only a kind of standalone kind of an area, but it can integrate with the IoT kind of thing. Okay, so these are the avenues where the people can actually go for a different kind of projects, and they can also work to find out more deeper thing into these. Okay, so and another importance, you can see that this graph shows the publication, the research publication that are coming with the last, you can see the one or 2 decades, 2000 to near 2019, and it is rising day by day. That means this area is very new and very important, and you have a significant kind of a growth you can see, and the data is according to the Web of Science. Now, as I mentioned that in these FDPs, we should actually look into the aspect not towards the research or the project base, but also towards the what are the teaching topics, or if you have a flexibility, you can also start running some new courses in terms of the electives. Of course, that the institutes which are affiliated to the universities, their university used to decide, but there are autonomous institutes where you can design your own curriculum. So you have a kind of the flexibilities available with you to frame new courses. So what is a broad kind of an aspect? What are the aspects to be covered under the flexible electronics? So you can see that because you have a kind of the bendable kind of a thing, how much the device can be bendable. So a lot of mechanics are involved in that. So one of the, you can say, the major module covered is in the form of the mechanics of the flexible electronics, because if you are installing any device or the circuit on a flexible substrate, so you are having kind of a bilayer. Okay, so bilayer, so what is the bending radius, what is the radius of curvature, then what is the flexure strength or the flexure rigidity of the device. Flexure rigidity is basically the resistance offered by the device when you actually put some kind of a stress on that. So this is one of the big you can say the module that should be covered in the flexible electronics. And then of course we have a different kind of materials and the substrate that actually take part or you can say are used in fabricating these devices. Because substrate itself is made up of different kind of materials, and these materials can also be used as an active material. And after that, of course, you have to actually give the connection to that. So all those kind of issues should be actually discussed in another module. After that, when you have a substrate and then you have an active material, then how to actually integrate that? What are the techniques? Like you might have heard about the spray coating and other kind of techniques. So, and other printing techniques like 3D printing. So what are the integration strategies? So that should be covered in this. And of course, when you actually dealt all the kind of this, the background, and then a lot of other devices should be covered in this in the form of sensors. So the main devices that are used are sensors. Then you have various flexible optoelectronic devices like organic solar cells, organic light emitting diodes, and the flexible displays, which are in the form of flexible thin film transistors. So this is the demonstration of what is actually meant by the mechanics and what is the substrate. So here you can see that you have a solid substrate and you have some kind of a dummy circuit that you have installed over the substrate. And in this case, if it is rigid and if you bend that, so this circuit will itself going to rupture. But here it should be in the flexible thing, the substrate should be bending, and accordingly your the circuit should also going to bend in that way. So that is what is meant by the flexible substrate. Now another term which can also be interchangeably used, but yes, there is a slight difference between the flexible and the stretchable thing. This is the demonstration of the device which is stretchable. When you stretch in this direction, so you have to actually prepare your circuit in such a way that it should not going to rupture. So these are the words that are actually interchangeably used. You might see a lot of other kind of the online courses on the printed electronics. So these are the few terms that are used: printed electronics, wearable electronics, or you can say the plastic electronics, flexible electronics, stretchable electronics. So these are the words that are being used these days for the new the courses in this area. Yeah. So when you talk about the first material to be coming on the flexible electronic devices is the substrate. So there are three important candidates that are used for kind of the substrate in the devices, and these are the ultra thin glass, metal foil, and the plastics, which are kind of a polymer films. So as compared to these three, the plastic or the polymer is going to outperform as compared to the other two because of these properties. Plastics having inherent low mechanical stiffness, so they have good thermal stability and good chemical resistance. So because of this, so this is mainly used for the flexible substrate as compared to ultra thin glass and the metal foil. But yes, of course, people have reported these two materials also to be used for the flexible substrates. And out of these plastics or the polymer substrates, the commonly used substrates are PET, polyethylene terephthalate, polyethylene naphthalate, PEN, polyamide, and its commercial name is Captain. Okay, so these are used. Of course, the choice of a particular polymer or the substrate is also based on that what is your application. Okay, suppose you are using the substrate for any flexible optoelectronic devices or the solar cell, so your first and foremost kind of a requirement is that it should be transparent. Okay, so you have to find out, then you will give priority to that kind of a substrate that which should be transparent together with the flexible. So, but in last 1 decade, there has been a significant kind of an upsurge for the research that is going on with the help of the new kind of a substrate, which is polydimethyl siloxane, and in short, we abbreviate it as a PDMS. The reason is that this material can be actually developed in a laboratory at a very low cost. This is one thing. Second is that it is transparent. Of course, it is flexible, and it is also going to have a lot of other properties which are actually required for an ideal substrate to be used. So, in our research work, we are doing a lot of work with the help of the PDMS. In fact, one of your faculty member, I think now he is not working here, Mr. Dr. Praveen Kumar Sharma. He did his PhD under me, and he did his work in the flexible antenna area by using this PDMS. Yeah. So, so what is the difference between the traditional as compared to the flexible electronics? And you all know that the traditional electronics basically dominated by the silicon. Of course, you also have a kind of a germanium, gallium arsenide, and other semiconductor materials, but mostly this is a silicon dominated. The reason is that it is abundant and easily available in the earth, and it's a high level of purity is also possible with this, and you have a well-defined electronic properties and consistency. So there is no need to actually again find out what are the properties of this material. So this is well-established properties that are known to everyone now. So also high quality contacts are possible with this. So traditional electronics is actually dominated by the silicon. Of course, you also have the germanium and gallium arsenide. So if you put together, you can you can classify them as a kind of an inorganic semiconductors. The materials, okay, the active materials as inorganic semiconductors. On the other hand, mostly the flexible electronics are made up of the mostly of the organic semiconductors. So the difference between the inorganic and non-organic semiconductors are that like the concept of the band gap is there in the semiconductors. So in inorganic semiconductors, you know that you have a valence band, then you have a conduction band, and all kind of physics is actually behind this one, which is actually discussed in the classroom to the students. But here in organic semiconductor, there is no such valence band and the conduction band, but even then we talk about the energy band gap. The reason is that these energy band gaps are actually formed because of the HOMO and LUMO. Okay, so lowest unoccupied molecular orbital, okay, and the highest occupied molecular orbital. So the difference between this is going to give you the energy band gap. And also there are a lot of other phenomena that are involved here. The movement of the carriers is because of the hopping of the charge carriers. So as you know that the organic semiconductors are basically the carbon based molecules with varying size that have a special chemistry that makes them a tunable conductor. Now, after covering these, you can say the 4-5 slides, now this is very clear that flexible electronics is not a standalone kind of an area which is actually being discussed by the electronics engineers. This is a kind of an interdisciplinary area where the people from the of course the electronics are there, then you have a lot of chemistry that is involved. Okay, so a lot of the chemistry is also there, then you have the mechanical part is also involved when you talk about the mechanics of the flexible electronics. So, so this is a kind of an interdisciplinary kind of the area, and yeah. So now I will talk something about the. Already I talked about that what kind of the modules, the structure should be if you are going for a kind of this area in terms of the teaching practice, and now I will discuss few research kind of a work that is going on. So mainly the devices that are fabricated with the help of this PDMS and kind of other materials. So you have this flexible strain sensors. So a lot of devices, I mean you can say the application part is there for this. You can see the application, the recently developed flexible strain sensors. So the working principle is that behind these devices is that when you actually give the strain to the device, to sensors, you will observe change in the resistance, capacitance, or you have the piezo electricity also. So you measure that parameter, and then if the response is changing, then you study. So I will cover that in subsequent slides. So but here you can see so a lot of application areas are available. You have a human motion detection here, so which can be installed on the virtual kind of gloves. Then you have a human machine interaction. In human machine interaction, what you do is that you prepare a dummy kind of a robotic hand, and that is going to mimic similar to you can say the functioning of the strain that are installed on a actual human hand. Then you have a lot of physiological signal capturing patches, root manipulation, then virtual gloves for the musician, then e-skin. So these are the patches that is there. So these are the kind of a few recent application area where you have we are using these flexible strain sensors. Similarly, the flexible pressure sensor devices are there, and this is also used for the human machine interface, health monitoring, and the wearable electronics. So this is the application part for the wearable electronics. So the temperature sensors can be developed by using these devices, and this is the e-skin where the different functioning healthcare kind of the, you can say, the application are being discussed here, and this is also there and suited for the lot of sports engineering kind of the area. And the working principle behind these flexible pressure sensor is that when you put a pressure, the mechanical excitation is there. So again you will going to have the change in the capacitance, resistance, and the other I mean mainly you have a capacitance or resistance change, and you capture the sensitivity of that. So this is what I was talking about, the working principle, the transduction mechanism. So in a simple sense, it is demonstrated here. So this is the piezoresistivity here. So when there is a strain, the mechanical excitation is there, then you observe the change in the resistance, because we know that the resistance is simply rho L by or L by sigma A. So change in the conductivity is there. So resistance change is captured, and change in the resistance by resistance is equal to the gauge factor into strain. Similarly, a simple capacitance formula, we all know the capacitance of a parallel plate capacitor is epsilon A by D, and so there might be change in the spacing when you put a pressure force here. So there will be change in the D will going to decrease. So when D will decrease, of course the capacitance will going to change, and also you might have change in the area of cross section A. This third one is a piezoelectricity, which is itself a property of certain materials the non-centrosymmetric kind of the materials, when you put a mechanical excitation, so these gets charged. Okay, so and the principle behind this is the piezo electricity. So the first, so these are the motivation why we are actually going to have these things, because all these devices have a lot of application towards the wearable kind of technology. So let us start with the kind of the first material that is used is the flexible substrate. So what are the properties that an ideal substrate should fulfill, or you can say in order to qualify to be used for the flexible electronics? So of course the first property is the flexibility, and the parameter that is actually govern the flexibility is the flexure rigidity, which is the resistance basically offered by the structure when you put pressure on that. So this flexure rigidity should, if the value is high, it means your substrate is not flexible. So you have to actually go for a lower value of the flexure rigidity. And then the elastic strain limit, to what level you can actually put a strain and it is not going to rupture. Okay, it should have a very high breakage point. And also there is another property which is actually can come inside this is the it's a restoring force. I mean, when you stretch that, it should actually come back to its original shape. Otherwise, when you stretch that, it will remain stretched. So those are the properties that you should have in this ideal substrate. And after that, when you are using this as a e-skin or the wearable thing, it should not have the irritation to the body, so it should be non-toxic. And of course, for the mass production, it should be low cost. On the temperature side, these are the properties. It should be thermally stable, and thermally stable means because when you have a substrate and it has to go to lot of kind of the other processing steps, so the processing step may be slightly at higher temperature, so it should be stable. Okay, it should not actually going to kind decompose or melt. And thermal conductivity, over the substrate you have another material, so the coefficient of thermal expansion of these two should be compatible. Okay, so that is a thermal kind of the conductivity, and of course low surface stiffness in order to have a better stick with the circuits. So but yes, ideal thing remains ideal. In practical, you cannot have all the properties coming in a one substrate, and of course we left this one. This transparency is, as I told you earlier, is required when your purpose is to be used for such application where you need transparency, for example the solar cells. So but many times many properties comes in, you can say the opposite sense. So a proper trade-off should be considered, and which property will be actually going to be working for you depends upon the particular application also. Now, as I told you that we are this in the polydimethyl siloxane, there's a lot of work that is going on, and this is a very recent material that is being actually used by a lot of researchers. So I'll be talking about the PDMS, polydimethyl siloxane. So this is the chemical, this is electronic structure of the PDMS, where you can see that the silicon is actually bonded with two methyl groups and oxygen atoms, and this N indicates that it's a single monomer, and you repeat this monomer multiple times in order to get a polymer. Okay, and this is these are the fabrication development steps for the PDMS. In this, we used to take the elastomeric base and curing agent in the ratio of 10:1, and this is the Teflon boat. Over a Teflon boat, we have kept the silicon substrate here. This is a silicon substrate, and after mixing it properly, we used to put this mixture in a desiccator to remove all kind of bubbles if it is having, and after that it is poured on this silicon substrate, and then it is baked to the hot oven at a very low temperature, and after that you can peel out of this, and you can see that uh, this is a flexible substrate that is actually prepared, and it is a very simple to prepare in the laboratory. So you can see in this animation, so this is flexible as well as transparent also. You can fold it into and you can fabricate a circuit on that. So this is how the PDMS, which is a very important flexible substrate, is developed in the laboratory.
There is any specific reason to use the silicon substrate?
Uh, no, there is no specific reason to use the silicon substrate.
So it means we may use a different kind of a wafer for create a
but yes, that is what I have shown you, that you have PET, PN, polyamide. So these are other possibilities that is there.
no, for the we are pouring a PDMS on a silicon.
No, okay, okay. This silicon wafer that you're talking about. Okay, so yes, for that actually the reason is that you can easily peel off. You can also do that similar thing on a simple glass, so that it can peel out. Otherwise, if in a simple plastic, if you are doing, it may get stick into that. That is the reason that it can simply you can peel out and then you can take out. That is the reason. I thought you were talking about the silicon. Okay, okay. So that is the reason. And its surface is very smooth. That is what. Yeah, so substrate part is done, and now above that you have another kind of material which is working as an active material. And so here you have a 2D, two-dimensional material. So this is the picture of 3D picture of the 2D graphene, and it looks like here as shown in this. And you have atoms. These are the carbon atoms which are arranged in a hexagonal kind of the arrangement, and these are the graphite sheets, and you extract this part from this to make it a graphene. So there are a lot of different synthesis method to bring this graphene from the graphite. Okay, and here you can see that in the next slide I will talk about the properties also, but what is shown here is the lower part of the conduction band is just coming over the valence band, and this is going to happen, this is going to take place at 6 places, okay, at 1, 2, 3, 4, 5, 6. So you can see this is perfectly touching into this one. So we can say that the graphene is having a zero energy band gap, but still it is not a metal, because in a metal you have a complete overlapping or the complete touching, but here in this case you have only 6 places. So that is why even we say that okay, the energy band gap for the graphene is 0, but it is not a metal. So when you wrap this, you can have the nanotubes. So carbon nanotubes are also used as an active material in this, and of course this is another allotrope of carbon. So this is the graphene, which is an allotrope of carbon, similar to the diamond, and as in the previous figure you have seen that you have a 2D atomically thick single layer of sp2 carbon atom. As I was talking about the properties, so these are the unique properties of the graphene that are listed here. So you have a zero band gap semiconductor. So this is a zero band gap semiconductor. So because this FDP is about the semiconductor, it is not that we only touched upon the inorganic kind of a semiconductor, which are the like silicon, germanium, gallium arsenide. So these are the other materials that are used these days in different kind of an application. So this is zero band gap semiconductor, and as I explained you that still I mean you cannot call them as a metal. Outstanding electrical conductivity is another unique property of this, and you can see that higher than copper. So we consider that okay, for the mass production we used to have a copper wire, but these graphenes are having conductivity higher than this. And graphene is also available in the form of ink. Okay, so there are various other applications where you need the graphene in the form of ink. In fact, in our lab also, one of the research student actually we developed that ink also. But yes, it is also available in the market, and is having very high electron mobility, and its thermal conductivity is very good. And because you have seen that all these properties should be there because to match with the substrate, so it is higher than copper, and is strongest material on the earth, and it has a low light absorption and insoluble in water, because you have to take care of the other aspect also when you are actually using these devices. So what is the impact of the humidity, what is the impact of the atmosphere? The device after fabrication should not actually deviate from its response because of these effects. Yeah. So any question till this? Fine. So in last to last slide, you have seen that what are the methods to synthesize the graphene, how you will going to get the graphene out of the graphite. So this is what is known as the synthesis growth or the synthesis. So majorly this is classified into two broad categories. The first category is the top-down approach, and the second one is the bottom-up approach. So the sense is very simple, that in top-down approach you bring the graphene from graphite by using the mechanical exfoliations or the chemical exfoliations. And this top down is a kind of, you can say, the small scale kind of a technique. And when you are doing some research in the at the laboratory level, then we prefer this top down approach. However, when you require this graphene for the industrial purpose, for the large scale kind of a production, you go for the bottom up. The meaning of bottom up is that here the graphene is developed from atom to atom. Okay, so atom, and then so that is going to you grow that, and the methods that are used for this is listed here. And out of this, the important one is the chemical vapor deposition. Now the CVD, chemical vapor deposition, is also available in lot of the institutes which have huge kind of the laboratory lab facilities. So for research purpose also, people are using the graphene that is actually being developed with the help of the chemical vapor deposition. And these are the other two kind of a variation depending upon the requirement: plasma CVD and the thermal CVD. For the chemical exploitation, though, I will discuss little about in the subsequent slides. So these are the other kind of the ways in which you can have. And in top-down approach, so after chemical exploitation, you also have a chemical synthesis in which we used to get the reduced graphene oxides. And reducing graphene oxide is also very important active material used in the flexible electronic devices. So I will discuss few of them just in a pictorial way. So mechanical exploitation is that you have a graphite, and the graphite is actually crushed in a powdered form, and then you have a scotch tape, and then just you put that tape here and then pull out. So you have an opposite forces. The forces are there in as an kind of van der Waals forces within the material, and then you put an opposite force, and this one layer will going to stick here. So you take this and then get deposited on the wherever you want to have like in the substrate or that. So this is how this is a conventional method to get the graphene out of this. So this is the adhesive tape. This is getting pressed, and then you have a few crystals that were attached here, and the tape with the few crystal layers was pressed on the target substrates. Okay. So this is the mechanical exfoliation process to get the graphene. And the second method is a chemical exploitation method, which is also known as the Hammer's method, and is more commonly term that is used for extracting this. So most common method for doing for getting the graphene sheet. So we start with the graphite, because this also comes under the top-down approach. You start with the graphite, and oxidation is done with the help of strong acids like sulfuric acid and oxidizing agent, and then you used to get the layered structure in this. And with the extended ultrasonication, this material is getting reduced to the exploitation of the graphene oxide. Okay, so you have graphene oxide sheets that are available after oxidizing this graphite. So you have a graphene oxide, and the structure of graphene oxides looks like this. In this, you have a lot of functional groups that are attached, like the hydroxyl group, acidic group. So these are the groups that are attached with the graphene oxide, and because of the you demerit with this the functional groups. We do not use graphene oxide. We have to reduce this graphene oxide. So what are the problems that are associated with the this graphene oxide? Is that due to the presence of these functional groups, okay, so these hydroxyl and these groups, so this is non-conducting, okay, and also you have a higher interlayer spacing, and the mobility is also very poor, and it is soluble in water and most polar solvent, which is not required, because once you actually place that on a substrate, the device may undergo various other fabrication steps, so it should not be soluble in water. And also you have a lot of other agents that are there for the processing. So these are the problems associated with the graphene oxide. Therefore, the remedy is that it is important to reduce the graphene oxide into the reduced graphene oxide, RGO. In short, we abbreviate it as RGO. And so this is our graphene oxide. So we have to reduce it with the reducing agent like hydrazine. So when you react this with the hydrazine, see all these hydroxyl, this functional groups and other associated groups will going to be removed, and the material that you receive after this is the reduced graphene oxide. And see the property after removing this will going to enhance a lot of improvement is there in the properties of the reduced graphene oxide as compared to the graphene oxide which are listed here. And the properties include that in the reduced graphene oxide, now the material is becoming biocompatible, and easily it can interact with the biological cells and tissues, because the device can be used for the healthcare for like the biosensors. So it should interact with that, and now it has become highly hydrophilic and forming stable aqueous colloids. So this has an importance in the large scale processing. Then the substrate deposition capacity is also enhanced, and so it's a great potential for the electronic coupling. So the reduced graphene oxide is a very important active materials in the flexible electronics area. As I mentioned that though CVD comes under the bottom-up approach, but these days with a lot of availability of CVD in the different research labs, you can also get the graphene out of the chemical vapor deposition. In this, the process is that you have to actually keep your you have to react this, or you can say you have to heat the methane molecules at very high temperature, 600 degrees Celsius. This is a pictorial way that is shown in presence of the metal catalyst. So this is another view of the similar kind of the demonstration, where the carbon atoms is getting detached because of this, and the metal, for example nickel, copper, and this all other materials are working as a catalyst. So you can see that atom by atom, when you cool down, atom by atom will going to form. So this is what is the bottom up approach. So you have grown this graphene by forming the atom to atom. Now with the perception that by doing this process you are receiving this, but you cannot see with the naked eye. So the researcher used to actually confirm with the help of the scanning electron microscopy SEM of this picture that whether the graphene is properly deposited or not, and then you can peel out of this. Now once you peel out of this, then how to actually transfer that? So this is the in continuation to that, you can see here. So you start with the metal, okay, so this metal, okay, metal wafer, and after CVD growth, so that means from here to here, that the process is actually there, this process is included, and so you will have a graphene that is going to go, come up with on the copper substrate. And after that, with the electrochemical delamination, you can remove this, and this graphene is coming here, and now this graphene is being transferred to the flexible substrate, and what is left is a copper, and again you can clean this copper and it can be reused. So in that way it is very effective. So this copper, this which is working as a metal catalyst, is getting reused here, and then the process is repeated. And what you are receiving after this is that the graphene is being transferred to the substrate, and this is one of the demonstration that is shown here, the transparent ultra large area graphene film that is transferred on this 35-inch PET sheet. And this technology this figure demonstrates that this technology of transferring is used in a lot of flexible devices, which include the organic solar cells, organic light emitting diodes, transistors, so these applications. Now your substrate is done. We have developed the substrate. You have seen the steps. Then we have actually received the one of the important active material, that is a graphene. The next thing is that how to actually print that, how the circuit is actually printed on that. So the printing technologies are very important to be discussed in that. And yeah, so broadly, printing technologies can be classified into two broad categories: non-contact printing and the contact printing. And so this is at the device level. But if you want to have a large scale production of these devices, for example, these days the solar cells can be made in this by using the flexible electronic techniques, then it is going to print similar to the printing machine that you have in newspaper printing. So roll to roll kind of. So it takes the concept of the non-contact as well as the contact. So that is why there is a connection that is shown here for the roll to roll. But as far as the classification is concerned, so this is classified into non-contact and the contact printing. Under contact printing, you have these kind of other printing that is there: screen printing, inkjet printing, and the slot die printing. So inkjet printing is a similar kind of a printing that you pour the ink on the inkjet printer, and that is going to print on, instead of paper, it is going to print on the substrate. Yeah, and in screen, okay. So I will discuss few of them in the subsequent slides. So in contact printing, you have the graver printing, offset printing, flexography, micro contact. So these kind of printing techniques comes under the contact printing. So this is what is shown in the form of the screen printing. So screen printing, all of us know that the screen printing is similar to what you have, you print your, you can say the card, okay, so using your visiting card or other kind of a card where you have a kind of a screen, and this is the active ink which you want to actually develop on this, and this is a stencil, and by using this blade you actually move this from this side to this side, and it is going to get printed. So a lot of the structural thing is included, and a lot of other ink, kind of the conductive ink that is shown here in another figure, the same conductive ink. And the parameters that are included in this is that this is that screen, okay, so this is the screen, and you have pressed this, this is the blade, and this is the conductive ink. So you are pressing it from here to here so that it will come on the substrate in a different stencil form, and this is the stencil that is shown here, and this is the active ink that is getting fabricated. This is one of the simplest kind of the screen printing process which is used to fabricate on the flexible substrate. Yeah. So these are the various parameters of what pressure you should give and what will be the contact angle. So that is there. So this is under the contact printing, graver printing, where you have a substrate that is placed here, and you have a graver cylinder, and the ink is actually kept in this. So you have a nozzle dispenser here, or a reservoir. This is a reservoir here, and the engraved kind of a cylinder. So the ink is poured onto this, and the purpose of this blade is that it is going to stop the excess ink that is coming here. Okay, so you can adjust this, and whatever, so you can see, if you see this part, so kind of a conductive ink is coming over the substrate, and this is the zoom portion of this one. And this is again another view of the similar kind of the graver painting. Yeah, so it has all kind of a technique will have certain limitation, that is for some devices it will going to be very useful, for other devices you have to shift for the other kind of a technique, like so you can use these graver printing to fabricate the bottom gated TFTs, ring oscillator, solar cell, and this one. This is the you can say the advancement of the graver printing in terms of the offset printing, where you have the same reservoir available here, then the same doctor blade, and the ink will be coming here. Instead of directly coming to the substrate, you have now included another kind of a blanket circuit, and the action that is actually taking place here is that now this ink is being transferred to the blanket cylinder, and you are drying this by using the ultraviolet dryer, and this roller is rotating, and it is actually having a complete kind of a web of the substrate. So this is rolling, so it is rolling like this, and then this is removing, and this is getting printed on this, and similarly thermal drying is done. So okay, so this is a flexography here. So this is a zoom portion, how it is getting transferred. So it is taking the ink here from this from the substrate here. This is the micro contact, which is a stamp kind of a thing, and this is the free polymer poured on the photolithography structure. Okay, so you develop a kind of a graved kind of a structure. So like we call it as a sacha. Okay, so that you actually fabricate that, and you pour the ink on this, and it will going to have that kind of a shape. And after that, so this is the curing of the pre-polymer and the peeling of the elastomer stamp. And then after that, the stamp that is received here is going to cut in smaller pieces, and then you have to actually dip this into the actual material, because this is a kind of a rubber kind of a thing, and then actual material which you want to actually transfer on the substrate, you pour that onto this one, and after that the stamp is inked by soaking it in an ink solution, and then you press that, and this structure will come on the substrate. So the technique is also very simple. This is known as a micro contact technique. So this is used for the printing that kind of device where you have the substrate and then active ink is coming on this. And this is another contact printing technique which is known as a transfer printing. This is a silicon on insulator kind of a substrate. Again, by using the photolithography, you have this kind of a structure. So this is silicon 100. Then you bring the PDMS substrate in contact to that, and then you actually press this. When you press this, so the compatibility is in such a way that when you pull out, so this material, this silicon that is there will going to come on the PDMS substrate. So this is one substrate from which you have actually grown the silicon, and this is another substrate you have taken out from this by pulling it from this one, and so after that you bring that on a different destination substrate, and you have this kind of devices that is possible. So you have different kind of a printing technique, and the people are also using the 3D printer to print these devices, and these days we are also going for the flexible silicon. Okay, the reason is now people are integrating the flexible thing with the silicon which is already available there. uh, I don't know whether you have seen the silicon wafer. Silicon wafer is already very thin, okay, and the our mechanics actually tells that the if you make any structure thinner, so it will become flexible. So if you actually grind that silicon wafer, okay, to a very thin, already it is thin, it's not very thick wafer, but again if you reduce that, then the silicon will become flexible. And the technical term these days that is used for flexible silicon is the ultra thin chips, UTC. So but those infrastructures that are available to do that is very expensive, but yes, techniques are available. People are using the benefits of silicon, and it is making available for the flexible electronics area by having these UTCs. So this is what a kind of a newspaper printing machine is there. Similar to that, where you have a large number of kind of the devices to be developed out of that. So that is known as roll-to-roll printing. So yeah, so in part A of the talk, we have discussed about the importance of the flexible electronics, that how this flexible electronics is used in different areas. Mostly it is used in the various flexible wearable devices, and the the substrate plays a very important role in that, and a lot of other possibilities are available for the substrate like P, TP, and PI. And for one of the substrate that we are doing in our laboratory is PDMS. So I have shown you how in laboratory itself you can grow the PDMS substrate. Then the active material is very important, which is a graphene, reduced graphene oxides. How to synthesize that is also being discussed here. And after that, what are the printing techniques? So a lot of printing techniques I have discussed. So this is part A of my talk. So let us have a break and then we will continue with part B and after 10-15 minutes.
One more question I
Yeah,
have in the previous slide.
yeah.
So there is photoresist we are using. Normally, if we are using a photoresist, it means we want to transfer a light, and photoresist will block the ultraviolet rays. So here it is. What's the use of photoresist?
Photoresist. Actually, what is there is that there is no board, otherwise I would have explained. Uh, okay, so if you have, let me use this dust. Suppose the structure is like this. So this is the SOI, silicon on insulator. So you have a buried oxide layer and then you have a complete silicon. Then you have actually make a mask of that. Okay, the mask is that you have these kind of rows. Okay, then you put the ultraviolet light. So light will pass through that. Okay, transparent areas, and then when you keep that into the etchant, so that will going to remove. And what is left is this structure. That is what is shown.
Kind of a structure only on the SOI.
Yes, yeah, that is getting developed after the photolithography. Yeah. Any other question? Yeah.
It is a silicon 100. Okay. So what is the meaning of this 100?
100 is the, it's not 100 actually, it is 100. It is the, yeah, Miller indices. This is a Miller indices. The reason is that this is one of the important thing that actually the student should know, that why all devices are fabricated on 100, not on 110, because there are a lot of trap defects available in 110 and other planes. And this has a minimum kind of the defects that is there. So that is why we go for the 100, and it is nothing but a Miller indices. So you might have HKL plane, if you know HKL plane, you know. Lattice structure, it has come from lattice structures. Orientation, okay, so that plane is taken. So basically it is a kind of a rod, if you see the fabric development of the silicon.
Lifted to the axis.
Okay, actually what happens that when you actually develop the silicon, it is not in a kind of a wafer. It is a kind of a complete huge rod. Then you actually cut that in, yeah. So you have to slice that like you slice the bread. Okay, you slice the, so that is actually kind of a wafer that you are getting. Now you are slicing it like this, or like this, or in this plane. You have a different orientation. 100, so this is 110, and this is different. That, so you have to take this cutting of this thing. That is the meaning of 100.
When the thing we want to generate a wrapper, there's a like ingot is there, like cylinder of the like. Cylinder is the fabrication is parallel. So we just slice the as per our requirement. So I need a 2 micrometer thickness, 5 micrometer thickness, whatever the size. According to that, they slice like horizontal.
So that is related to the surface area.
Plane. Okay. So we'll discuss part B.
After 10
Okay, so welcome back after the break. So the part B of this talk will be mostly on one kind of a device, that is the flexible electronic sensors. Because in part A we have already covered the substrate materials that are used for the flexible electronics, the active materials that are used. In fact, we have discussed a lot about the graphene, but then you have other active materials also that are used as an active material. Apart from graphene, you can also have carbon nanotubes, CNTs. Then you also have the transition metal oxides, TMOs, then transition metal dichalcogenides, TMDs. So those are also possible. Okay, so yeah, so this is what we have already covered, the development of the PDMS. This is how you can fabricate, and this is the animation part that I have already shown you. Now, once you have developed that, so you need to actually analyze, you need to test the properties of the substrate that is developed. And so for that, we have developed the acrylic mold. So this is an acrylic mold which is developed by using a CNC machine. And here the length of the, you can say the PDMS is kept as 30 mm, and the width is kept as 5 mm and thickness is 2 mm. And after that, so this mold is kind of the step that you can assume that till here, and then you are pouring that PDMS on this. So similarly, you are pouring that PDMS on this mold, and when you actually peel off, so this is the PDMS that is taken out of this. And now why this dumbbell kind of a shape is given here, so that you can easily clamp this on the machine and you can stretch that. So for getting its mechanical properties, because we want to check that whether it is quite flexible or not. And already I mentioned that we used to have the mixture of base and the curing agent in the ratio of 10:1. But why 10:1 only? So for checking that, we have fabricated 5 samples taking different ratio, 5:1 ranging to 25:1. And this is the Mark 10 instrument setup for checking the mechanical properties. And you can clamp that here, and then you can push that, and you can measure the strain and the force that you are giving, and you can get the mechanical properties. So the properties that we have captured by using this as shown here. So the stress versus strain for different ratios. Yeah.
We are using a PDMS. It's a like a round type of, and we may cut in a dumbbell set, like that kind of shape of a PDMS.
That is also possible.
So we,
For that you have to actually take a rectangle kind of this thing, and then you have to cut very precisely. So that is also possible.
because for this one we first
Why we actually build the this thing, the mold is because we have developed one circular kind of you can say the PDMS for different purpose. So we have taken this mold, and then because the pouring is done, because you can pour that in a complete rectangle, but that PDMS is not when you have to buy that. So when you are removing, that means you are wasting that part, no?
at least like extra.
So you cannot reuse that. That you have to remove that. Yes, your purpose will get fulfilled in that way, but then you are removing that. That cannot be. You cannot melt and again you cannot use. For that, mold is the better choice. Yeah, so this is the mechanical property that is shown for the different base to curing agent ratios. And here you can see that the tensile strength is 3.38 for PDMS 5:1. And when the ratio of this is increasing, you can see that the tensile strength is decreasing here. In fact, the Young modulus is reducing. So the reducing Young modulus is better for the flexibility. That means it is becoming less stiffer. So that is stiffness is reduced, and which is one of the requirement for the flexible substrate. So this is good, which is actually taking place here. And elongation break is also increasing. So that is going to actually break after this much, the stretching of this sample up to this limit. But then your tensile strength is reducing, so somewhere you have to make a compromise in that. So for that purpose, in a lot of literature, you will see that the PDMS is actually used to have 10:1 ratio. Now after this PDMS, we have fabricated a strain sensor with the help of the graphene nano pellets. So this graphene nano pellets is purchased. This graphene nano pellets is purchased from the market, and then this is the PDMS, and the spray coating is done in order to fabricate this. So this is an optical photograph that you can see here. So this is just a kind of folded one, so that we can demonstrate the flexibility of this. So when you stretch this, so you can actually get the information about the strain, strain to be used in different other calculations. So you can see that you can twist this, and you can stretch this also, and after that the measurement is done. In fact, the contacts to the device is made with the help of copper wire, and it is attached to this one. Copper wire is actually fixed here with the help of the silver paste. And after that the measurement is done with the help of the multimeter here that is shown in this, and this is a complete setup. And with respect to the strain, we have measured the change in the resistance, and the change in the resistance divided by the R naught, that is the original resistance, is plotted here. And this is the parameter which is the measure of the sensitivity. Basically this delta R by R naught is equal to the gauge factor multiplied by strain. So that indicate that the slope of this, and the ideal kind of a response that is expected is a linear. So this is almost kind of a linear. You can draw a straight line out of this, and the slope of that will going to give you the gauge factor. Now the gauge factor that is actually required for these kind of a devices it should not be too low like metals, which is 2 to 3, and should not be very high like for the semiconductor it is about 100. It should be nearly 50 to 60. So in this case we got 62.5, which is as expected here. And after that we need to check the response of the sensitivity with the stretching and releasing. So we have stretched this, and then we have measured and the stretch and release. So this is one cycle, and this is 2 cycles that is shown here, and you can see that complete kind of a reversibility is there. Okay, it is not that once it is stretched it will remain there. So that is also a very important checking, or you can say the testing of the flexible devices, that you should check that on how many cycles. Ideally, for some of the devices we have checked for the lot of cycles, because if you are using these devices for the flexible purpose, so many times you will be using this. Okay, so it should not be that for after a certain interval it will going to break. So that is there, and this GNP based device that we have developed is demonstrated for the wrist pulse sensor, which is shown here. In order to compare this combination, we have grown this GNP on the ready available substrate, that is PET, and this is the polyamide, and this is the carbon fiber. And you can see that a lot of noise and the disturbance is available in other kind of samples, where the GNP that is grown on PDMS, you can see the curve is very smooth, and if you zoom this portion, you can see that the standard pulse can be seen out of this, where you have the P wave, T wave, and all these kind of signals are available, where here you can see that all these kind of waves are kind of a distorted one. So this gives the confirmation that the GNP that is actually grown over PDMS is working fine as a pulse sensor. So this is one kind of a device where we have developed the this GNP based PDMS. The second type of device that we have fabricated is the graphene PDMS flexible sensor, and these are the fabrication steps that are shown here, where the CVD is grown. Graphene is grown by using the CVD, and So you can see that this is already in part A of the talk. It was discussed that the graphene is being deposited here atom by atom on the metal, uh, not substrate. Basically, here the metal is working as a catalyst, and after that you pour this your PDMS on the this graphene that you have here, and then there's a spin coating, and there are a lot of heat treatment also that is involved. So we used to heat this for 30 minutes, 80 degrees Celsius, and then it is kept in the copper etchant to remove the extra kind of this thing, copper that is there. And after washing this, so this is the device that we have, and here it appears to be shorted, but yes, this is cut from this. So these are the wires that are given for measuring the parameters of this device. This developed flexible strain sensor is used for the human motion detection, where the device that is developed is placed on the elbow, then on the finger, and on the wrist. So here the resistance is very large, because here the bending is high as compared to the bending that is there in these two cases. So we want to check that what is the bandwidth of this sensor, that whether it can sustain a large strain or not. So for doing that, this testing was done. So we tested by placing this on the elbow, and again with respect to the time, we have measured the sensitivity, that is the change in the resistance by R naught for this, while after bending the finger, and the pulse in this recognition of the wrist bending. Basically we have captured this one. So here we can see that the device that we have fabricated based on the graphene is going to capture the very high resistance, high stretching to the low stretching. The resistance measurement is possible with this range. Then this graphene based device can also be used for the dry electrodes. Now what is the purpose of dry electrodes? Because we have seen that when you go for doing the ECG, then the medical person used to have kind of a conductive gel. Okay, they used to place a conductive gel, and then they used to place an electrode. So those electrodes are silver chloride based electrodes. So the demerit for that is that many times this conductive gel gives the irritation to the patient, and lot of uncomfortabilities there for the in that case. So we have proposed that we can remove all those kind of things, and we can use these patches that we have developed as a dry electrode, where you do not need any kind of a conductive gel that has to come in between the human body and the electrodes. So this is what is fabricated here, graphene based dry electrodes, and the fabrication steps are shown here. So again we start with the Teflon boat, then we use the silicon wafer so that we can easily peel out of this one, and this is the male snap button. So in the gel form itself we have kept that button, simple button that we have, and after leaving that for 30 minutes you can easily peel off this one, and you can see that this is the PDMS and the male snap button is there. And after that the graphene is deposited on this one by using a conventional spray coating method. So in this case this is a reduced graphene oxide, because in the first part we have seen that how the reduced graphene oxide performs better as compared to the graphene also. So this reduced graphene oxide based PDMS dry electrode is fabricated in this way, and this is the electrical part where we have modeled the human skin. So this is the electrode thing that is coming here, and these are the different layers of the skin. So we have modeled that in terms of the electrical parameter. For that we have done the impedance measurement to extract these RP, CP and RS. So that was extracted in order to get the impedance of the electrode. Of course, after that the experimental setup was done. So by using the Arduino, so that was actually programmed, and here you can see. So this is the electrode that is placed here, and then measurement is done. You can see that by having the real-time monitoring, and this is the these are the patches. So this one are the reference kind of a patches. I mean, reference means AgAgCl3, and these are the electrodes patches that we have fabricated. And for measuring that, volunteer of 28 years male person is taken here, a healthy person, and his ECG was measured out of this, the developed electrodes. And this is the monitor where we have captured, and the outcome that is received in this is shown here. So the top one is for the AgAgCl electrode, okay, the conventional electrode that is available in the market, and this is the response of the electrode that was fabricated in the lab by using the reduced graphene oxide PDMS dry electrodes. And if you zoom this portion, zoom this, and it will look like this one. So where you have a standard P kind of a pulse, then the QRS pulse is there, and then T pulse is also visible. However, if you see this one, this is not that smooth to this one. At first sight, you can see that okay, this is something that is more disturbance is present there. In order to confirm that what is this actually happening here, and a very smooth kind of a pulse that is observed in case of the dry electrode, we have done the measurement of the signal to the noise ratio. So signal to the noise ratio for AgAgCl electrode is shown here, and this is for the fabricated reduced graphene oxide PDMS based. And this is the formula that is used for measuring the SNR, 20 log to the base 10 Vs by Vn. Basically, we have measured peak to peak signal, this one divided by this. You can see that the peak to peak signal divided by this one is, so there's a lot of noise that is available. That is why this value for this case, that is a reduced graphene oxide PDMS, comes out to be 27.2 dB, while for AgAgCl electrode, this comes out to be 25.7 dB. So this property also confirm that this dry electrode is a alternate choice and working very fine as compared to the already available AgAgCl electrodes. Yeah. So to yeah, of course, in one of the slide I will show you that in fact, as an electronics engineer, we can just see that okay, the pulse is going fine, but how to differentiate between the pulse that is you are getting for a healthy person and if abnormality is there. So in one of the slide I will show that what are the parameters that is actually captured once you have these kind of pulses. But before that, let us try to see another kind of a device which is developed with, not with the help of the graphene, but with the multi-wall carbon nanotube. Okay, so tetrahydrofluorine mixture is kept here, and in that you have the multi-wall carbon nanotube. That mixture is magnetically, you stir that for 20 minutes so that the proper mixing is there. In that mix, you have to actually first pour the PDMS base, and after that you pour the PDMS curing agent. Okay, and then you can develop, you can actually pour that on a mold, and then again you have a kind of a sensors that is there, and this is silver paste, and the wires are coming out of this. This is a set kind of a practice when you actually have kind of a composites, because in this case it is not a layer by layer kind of, okay. You can see that it is not that first we have developed the active material and this is actually pasted on the substrate, because here we have actually putting the drops for this one. So that means this is a composite. So in itself it is there. So if you target for a composite, so it is very important that you check whether the proper mixing is there. So this is a set practice that you go for the testing its surface morphology. So surface morphology is done. So this is one of the important characterization technique, and you can see that we test that whether the proper mixing of the multi-wall carbon nanotubes and the PDMS is there or not. So after confirming that, then we proceed further to get some other kind of the analysis parameters. Again, as we did in the earlier case, so we developed this kind of the mold, and the dimensions were kept as same: 30-meter length, 5 mm width, and 2 mm thickness. And another mold is developed, and using that we have poured that this PDMS. This is a only PDMS, and this is that combination. This is the composite out of this. Uh, so these samples were prepared in order to get the various other parameters. So to check the flexibility and to check the different carbon weight ratio, because this is a kind of a one go kind of a this thing, but in what ratio you are adding that. So that is also important. In order to test that, so we have taken the 2 weight percent of CNT, 4 weight percent, like that. So using this, we have measured the parameters again with the help of force 10 measurement setup. So you can see that with a simple PDMS, these are the properties for base to curing agent as 10:1, because that is already decided in previous testing that we have to take 10:1 PDMS. But in that we are actually coming up with the composites. So in what ratio you will be adding that? So that is actually tested here. And you can see that when you increase the CNT level from 2 weight percent to the 10 weight percent, your tensile strength is increasing and your young modulus is increasing and elongation break is going down. So that is how after a certain limit, because as I told you that the getting the large value young modulus means that your sample is getting stiffer. Okay, so this is how the young modulus that is actually calculated here is shown. And then this device was tested for the cyclic loading. So we have loaded, unloaded several times. So you can see the 3000 seconds. So this is a complete kind of a band that is showing here. But if you actually take out this part and zoom it, this part, if you zoom it, it will look going to appear like this. Similarly, at a later time, if you take this one, again, it will going to show it in this way. And at a this range, you will going to see. So what is the observation that we are getting here? That when you load, unload, the response remain the same. It is not that with these kind of cyclic loading and unloading, the response of the sensor is going down. So the response will remain consistent, and which is the main requirement for the device that you fabricate, that should actually work for the longer time. So this was also done in this. And then because this was developed with the purpose of pressure sensor. So the first device we have used as a wrist pulse sensor. Second device was used for the dry electrode. Then the third device, which is multi-wall carbon nanotube based CNT, this PDMS. So the main purpose for this is to work it as a pressure sensor. So to work it as a pressure sensor, that is why in that slide you have seen that we have a circular kind of sample, because we want to check what pressure you are giving and what is the measurement that you are taking out of that. So this is that sample, 30 mm diameter is taken for this sample. So again, this is developed by using the CNC machine, and so this is kept on this, and on the back side you are giving the pressure. So what pressure you are giving is being measured by the pressure gauge, and the response of this with respect to the electrodes that are placed here and the wire is coming out is being measured pictorially, or you can say that schematically it is shown here, that this is that sample, the layer that is placed here, and from this side, that is from this side is you are giving the pressure, and of course this deflection will going to take place and the measurement is taken. The measurement is taken again in the form of the resistance, and these are the pressure level that we have given. So from this 20, 40, 60 up to 100 kilopascal, and with a different range of this one is shown. Now this is what is shown here is kind of an hysteresis, that when you actually stretch, you increase the pressure, and then when you decrease the pressure. So ideally, if your sensor is working ideally, it should follow the same path, and this is what is known as a hysteresis. So hysteresis is another parameter for getting the analysis about the sensor, that the hysteresis should be as low as possible. So, but ideally it should be a straight line, so it should follow the same path, and but that is not possible. But what you can do is you can minimize that as much as possible. So this curve is actually showing like, so you can see that the arrow also going to indicate, okay. So this is what the hysteresis is shown, and you have a change in the resistance that is shown here. And the sensitivity is plotted as compared to the different weight percentage of the multi-wall carbon nanotube. The actual sensitivity of a human skin ranges in this range, and with these 2 weight percentage in this one, you can see that almost we are getting. So what ratio will be perfect? So this will going to decide. So that is what you have to pick, that kind of the weight percentage which will come in this range in order to check that. And of course this is already being demonstrated, and the sensitivity can be expressed in this, and here one delta is coming extra, so this is a typing mistake. So S is equal to delta by R naught by change in pressure. So this is how the sensitivity measurement is done. Yeah, so this is what I was talking about, that once you have the pulse, ECG pulse or the wrist pulse that is coming here, so this is now a task of a clinical expert to check whether the ECG is of a healthy person or the some problem is there. So from these waves, so we have two parameters that is extracted by the person. So what they used to do is they used to check the ratio of this pulse. So P2 by P1. So P2 by P1 is known as the radial artery augmentation index. So this ratio is measured. So they used to check. So because they are so expert that just by looking that they can tell you that okay, is abnormality is there or everything is perfect. Second parameter is the gap between this pulse, the peak and this peak. So this is known as the time delay between the precursion wave, delta t. So for standard, for a, you can say the healthy person, so these are the values that we have actually received. If this is very far or very close, so then the clinical experts will going to test and will going to give you that kind of the result out of this. So here you can see that these flexible electronic devices can be used for different ranges, and the purpose of now the flexibility is very clear, because every time you are actually using this for some variable kind of a purpose, for that it should be conformal to the body dynamics. So that is why it should be like that. And yeah, so this is the conclusion. And so we have seen that what are the future perspectives of the flexible and stretchable sensors for the wearable health monitoring, and the transaction mechanism behind that is piezoresistivity, capacitance, and piezoelectricity. And we also seen that PDMS is one of the very important flexible substrate, and you can fabricate that in your laboratory. So there is not much kind of the infrastructure that is required for developing the PDMS. 2D material, one of the important 2D material is a graphene. You can extend this by getting the reduced graphene oxide, and we have discussed its properties and the different synthesis kind of a methods, and the application of graphene with the PDMS is also discussed. And we have seen that what are the various printing techniques that are there to integrate this one, and the design of various other devices we have seen in terms of the pulse and pressure sensor, pulse sensor, and then the dry electrodes. So we can say that the flexible electronics is kind of a game changer in the world of technology, especially in the health care sector. So thank you for your patience. So if you have any query, or kind of, and I mean, already you know that we have a very good collaboration with the BKBIT and our institute. So many faculties are doing research, already they have done research. So some facilities are available here. We are also taking help of the Siri Pilani. So you people are also
My question
yeah.
is regarding the strain
just like in a slide, you are just putting a paste over here on the elbow side, maybe on a wrist side. So if strain is generated, so it is depends on an angle. So it means more like this
Yes.
angle is 90 degree.
Yes.
So you may paste here, it is another angle, another angle. So it means human body is like any joint, not more than like 45 degree may be flexible. So if we increase an angle, so it means like characteristics or maybe ECG pulse wave is a different kind of.
ECG will come because of having the electrodes. So that measurement is different part. Here, like you said that for the different parts, you will have a different kind of a stress. So that is what we have checked in one of the case, that whether the fabricated sensors can actually sustain that kind of range or not. So like in elbow, you can have, okay, so like this, and the finger also, though I have not shown the result, but as you said that for different angles, we have actually captured this ratio.
Like it is better to like implement that sensor on a different angle. Like we will prepare some kind of a model, then we start from the 0 degree angle to and then 90 degree angle. Other than like on a put on a.
That kind of study is also.
So it may be like different kind of characterization of that strain.
Yeah, we have also done that kind of a study. That is also there. Yeah, any other kind of a query?
Thank you, sir.
Okay.
Sir, I have a question based on the graphene sensors. So, what is the durability of these sensors? It is
Yeah.
for a longer use?
Yeah, for the durability, you can see that we have checked its the cycles. Okay, its response with respect to the number of times you are loading and unloading. So we have intentionally given the loading and unloading for 3000 seconds. Okay, but in actual practice, you will use at some other time, or maybe, so that 3000 kind of a second time will come at a very after a very long time. So for that purpose only, whether it is durable or not, we have given that, we have tested that. So you can see that the response is uh, same. This one, this. The peak to peak and this measurement is same when you have the loading and unloading of 500 second to this one to this one. So this actually demonstrates that it is durable for a long time, and you are getting a similar kind of a response.
And sir, what is the response times of it? Like if I'm creating a sensor with the help of graphene or any electronic semiconductor devices, so what will be the time delay in that?
No. I mean, here the comparison is not in terms of the that kind of an output. Here the purpose is different, because for the conventional semiconductor, if you are using those sensors, you cannot place that, because those are actually built with the help of the bulk silicon wafers. So you cannot actually. So it will be, if this is rigid, so it will come like this. So here it is, the conformity is the important issue in this. So, if no questions, so thank you. Yeah.
That we saw all sort of positive aspects of flexible electronics.
I don't want to sound pessimistic, but do we have any sort of drawbacks or cons of flexible electronics that it is not capable of doing? Or any sort of challenges that...
Drawback is that because the silicon-based technology is well established.
Drawback, why we are saying a drawback, because drawback it means it is like a research area for us. It means if you are saying that this is a drawback, that means it is in our mind, it is a plan. It means we want to work on that drawback.
Drawback in that sense, it is, because you have seen that drawback in terms of the nanomaterial itself is kind of supposed to be to be handled very carefully. Okay, so that is a kind of a drawback, that when you are actually working on that, you should take precautions to actually fabricate those devices, because those material itself is toxic. Though the PDMS is not toxic, but yes, graphene and other material, carbon nanomaterials, are to be handled in a proper way.
Thank you, sir.
Okay, thank you.
Thank you, sir, for your enlightening session. Now, I would like to call up Dr. Nimish Kumar, HOD, Computer Science Department, to honor our distinguished speaker with a token of love. Thank you very much, sir.